Okay, yesterday we started chapter 10 a little bit. I just want to go back over that since Nick wasn't here, and we want to make sure that we do this. And yes, we are doing this for Jacob because we miss you, and we hope you come back and have accomplished what you wanted to accomplish. There we go. All right, so yesterday we started chapter 10 on energy, and I explained how energy is anything that has the ability to cause a change in itself or its environment. So many different things will contain energy as long as they can cause a change. We began introducing kinetic energy, the energy of motion. Most of you have heard of that before. Kinetic energy is measured in joules, and all energy is measured in joules. The calculation is 1/2 times mass times the square of velocity. Okay? And then we moved on and we got a definition for work. Yes, this is review. We had a definition for work. And work is the force times the distance that the object has moved. Force times the distance that the object has moved. Now it's important to remember that the force and the distance of motion have to be in the same direction. It's a straight line direction in order for it to count as work. So in order for me to do work on something, the force that I'm applying has to be in the same direction as the motion. As a little bit of an additional example, if you lifted up a barbell off the floor and you were holding it at the end of your arms, the process of lifting it from the floor would be work because your force and your distance are in the same direction. But then if you walked around with it all day, okay, the force is upward because you're holding onto those barbells, but the distance is sideways, so it wouldn't be considered work, even though it would wear out your muscles. Okay, so work has to be force and distance in the same direction. Okay, the equation work equals force times distance. A Newton meter is an alternate to a joule. So 1 joule is 1 Newton meter. 1 joule is 1 kilogram meter per second squared. Work and energy are very closely related. The joule is named after James Prescott Joule, who did a lot of discoveries on this particular topic. And then the last thing we said is that work and energy are so closely related that if you have a change in the kinetic energy, that equals the work done. Or if you do work on something, then it causes a change in its energy of motion. Okay? And this is just reiterating that idea that work is done only if the force and distance are in the same direction. So where we are on this is we need to work through some examples, some problems. So here's an example problem. Okay, so let's get this written into your notes. A 105-gram hockey puck is sliding across the ice. The player exerts a constant 4.5 Newton force over a distance of 0.15 meters. How much work does the player do on the puck? And what is the change in the puck's energy? Okay, now that everybody's got it written down, 105-gram hockey puck sliding across the ice. Now it's asking first how much work is done on the puck. So we have the equation for that, which is work equals force times distance, as long as the force and the distance are in the same direction. So which one of the two things is causing the hockey puck to move? The 4.5 Newton force from the player, or the fact that the hockey puck has weight?
Because the 4.5 Newton.
The 4.5 newtons is causing it to move this far. So our work then completely ignores our 105 grams. We wouldn't even need to have that. The only reason it's in this problem is because in real life you encounter information, you have to be able to sort out which is relevant and which is irrelevant. So 4.5 newtons times 0.15 meters, and this is a nice problem. It doesn't even mean that you have to convert anything. So 4.5 times 0.15 equals 0.675. And what's my unit for work again?
Joules.
Joules. Okay, so this is the answer to the work, 0.675 joules. So what do you think about the second part of the question, the change in the puck's energy?
You would solve for K and then change in K would be
Remember our work energy theorem? It says delta K equals what? Work. So it's the same thing. The change in the puck's energy, delta K. So this is the same answer. Because delta K, which means this, change in kinetic energy is the same as the work. So actually that puck had 0.675 joules of energy added to it. So that would affect its velocity, it will affect its momentum as well. Okay, where did I lose you, David?
It's the change in the puck's energy.
Do you get this part?
Yeah, I got that part.
Okay.
How's that the same?
This is just, we're going to think of it as a synonym. Okay, just like when we had the other theorem in the other chapter, it's asking the same question in a different way. Here's our work energy theorem. Delta K, which means change in kinetic energy, equals work.
May I have your attention, please? When you're high, girls.
All right, so you lift a 102 kilogram scooter into the back of your pickup truck. The bed of the truck is 0.8 meters from the ground. How much work do you do to lift it into your truck? Okay, so we need to calculate a force times a distance, right?
You need no force.
But we don't have a force.
But you have.
We do have a mass, though. Okay, so what force are you going to have to overcome in order to lift this thing up?
So you put a mass times
Gravity.
acceleration. Acceleration is gravity.
Right. So we actually need to find the weight, or the force because of gravity, on the scooter. So Fg, if you remember from the other chapter, is mass times little g, which is
9.8.
9.8. Good. So we have a 102 kilogram scooter times that 9.8 meters per second squared. And we need to do that calculation.
That would be 1.
And we get, about 1,000. 999.6. Yeah, it's about 10. So there's our newtons, how many newtons it would take to lift that up. So now we can use this equation. Work equals the force that we need, which is 999.6, and the distance that it was lifted, which is 0.8. So
799.68.
Yep. We'll just say 799.68 or whatever you want to do there. And the work is measured in the unit of joules. Okay, so now in this case it's being lifted upwards, so the force and the distance is in the same direction, so you are good. Now just be careful that you always take notice of whether you're given the mass or the weight to start with, because if you're given the weight to start with, don't multiply it by 9.8 first. Okay? always take special note of that.
Yeah.
Okay, because that can really mess up your problem. Okay, so you can have a reverse question on that. You could ask how much work gravity does. I'm just going to try and write this one out here. Let's say we have a 3.9 kilogram bowling ball. Okay, that's pretty light one actually. Drops from the second story window. That is, let's see, 5 meters from the ground. How much work, what would be doing the work on that falling bowling ball?
Gravity.
Good. How much work is done by the ball? Work is done on the ball by gravity, and you can ask that. Yes, we will have a force, and then we have to have also the distance. Okay, so you do have to take into account the actual weight of the ball. Okay, and then you have to take into account the distance that it fell.
Doesn't matter positive or negative.
We don't have to worry about that for this. Okay, because they're just asking how much work is done. Technically, work is also vector, but we're just going to get a number on this one. So our work equals force times distance again, right? So our force is going to be Fg, so our mass is 3.9, multiplied by what?
9.8.
9.8. So 3.9 times 9.8 gives us 38.2, or what we say about, yes, about 38 newtons. So our work equals 38 times what? 5. 38 times 5. So 190. 190 unit joules. So in this case, once again, you need to be really careful. Watch your units. Watch what you're given. Watch what you're asked to find. Okay, let's get another type of example.
Can you go like 5 seconds? Like
Sure, I can wait.
20 seconds.
All right. So you can be asked another type of question too. You could say that something, and I'm just making it nondescript, something was lifted 4.3 meters using 9.0 kilojoules of work. Okay. And so you can say, what is the mass of the thing that was lifted? So we have to work backwards on this one. So this would be another work equation, right? So what equation do we start with?
W equals F times T.
Okay, so W equals F times D. So our force in this case is,
We don't know.
we don't know.
We don't know.
Do we know the work?
Yes.
The work is what?
9,000.
9,000. Remember, kilo means thousand? So it's 9,000 joules.
Not joke.
And our force is unknown, and our distance is 4.3. So our force is, it's a pretty simple calculation here. 9,000 divided by 4.3. You see in 2093. What's my unit on my force? Newtons.
Gotcha.
Okay, force is in newtons, but
Sure.
we're not there yet because it says what is the mass. And mass is measured in what unit?
Oh.
Kilograms. So what we just found here is what?
The force. The mass
Force.
times the gravity.
Good, the force of gravity pulling on this mass. So we just found Fg.
Oh, yes.
So we just found 2093 equals something. It equals
Mass.
Something divided by
mass times
9.8.
9.8. So the mass has to be 2093 divided by 9.8. And we get 214. What's my unit for mass?
Oh, it's kilograms.
Kilograms. So this was a pretty good size something. Roughly 400 pounds. Roughly 400 pounds.
Wait.
Okay.
Where's the microphone?
Okay, thank you. All right, so the other thing we need to do is take a look at what happens if you're putting a force in through an angle. If you're putting a force in through an angle, then possibly it's only one direction of the force that's going in the direction of motion. Let me give you an example. If we have a guy pushing a lawnmower, okay, there's the guy, and he's pushing the lawnmower. And so it's got the handle to the lawnmower here. Okay, and it goes down, and it's attached to here. Okay, he's pushing with one hand, wheels on the lawnmower. Somewhere there's blades under there that are chopping up the grass and sending it flying all over the place. Okay, all right. But we have this, and he's pushing down. His force is divided up into two. He's got a downward force that he's pushing, and he's also got a sideways force. So we have to have a way of breaking that down because it's only the force that's sideways that's causing the lawnmower to propel this direction. Okay, does that make sense? So we have to be able to deal with force at an angle. All right, let's get past my lovely picture here. And say that we have a force that's being applied at an angle. So maybe we have, here's my force. I should have done that. Okay, and say that this one is a 320 Newton force. And this gets broken down into its components. We have a sideways component, and we have a downward component. Okay, it's meant to be a right angle. I didn't quite get it. Pretty close. All right, and let's say that the angle here, let's say that that's 31 degrees. 31 degrees. So you very, very precisely measured this for whatever reason. Okay, and let's say that the object, whatever it is moving to the right. Is moving right. And goes 15 meters. Now we need to find the work. Okay, so if we've got this situation, which component of this particular scenario is going to be important for calculating the work? This one, right? So we care about the x component. How do we calculate that x component?
Cosine.
Cosine. Good. The cosine of 31 equals what over what? X over 320, absolutely, Gary. So we have 320 cosine 31 equals your x component. So x equals 320 cosine.
Cosine is the function.
Yeah, it's gonna be fail.
And that's 274. 274 newtons. So my force equals distance, force times distance. No, I'm sorry, not the force.
Work.
I mean work. Work equals force times distance. So work, our component is 274. And the distance moved is 15. So 274 times 15, which is going to give us 4114.
Joe.
Well, wait.
41?
I just did answer times 15. 4110 for the rounding. Joules. Okay, now there is a little shortcut to that equation without having to do it in two parts. Okay, and let me give you that formula just real quick. It comes out to be that the work, when there is an angle between force and displacement, can be shortcutted. And you can do it in one equation, which is work equals force times distance times the cosine of theta. Force times distance times the cosine of theta, without having to think so much about all these things. You can just write this equation right down, and it is right on your formula sheet for when you do those type of problems.
So it's always going to be cosine no matter what?
Yes, as long as you're looking at an angle from the horizontal, which you will be in these type of problems. So you are now equipped to do the problems 1 through 8, and that's what you should be working on, is problems 1 through 8.
Just in